Geometry 12.4 Part 1, talking about angle measures within circles. This is a tough section here, guys, so we're going to try to break it up into two parts and just do half of it today and the other half of it tomorrow. So the first theorem we have to talk about here today is Theorem 1213. This is what happens here, everybody, when we've got lines intersecting inside a circle. And a few theorems we're going to talk about later deal with what happened when they intersect outside a circle or even on a circle, which we've seen before. So this theorem right here, everybody, 1213, right here, says that if two lines are intersecting inside of a circle, and as you can see right here, the only kinds of lines that intersect inside of a circle are going to be tangents. Although if we cut the arrows off, we could make chords out of this as well. Then the following is going to happen each time that we do this. What we're going to see here is that the measure of one of our angles formed right over here, this one x, is related to this arc here, which is A, and this arc down here, which is C. Now these are not, x and y, these are not central angles, you'll notice, because their vertex is not located at the center. So what happens here, everybody, is that the measure of arc x, we're talking about right over here, is going to equal the sum of A up here and C, and then divided by 2. So this formula is going to be an A plus C all divided by 2. And what we're doing when we take the sum of two numbers and divide it by 2, we're really taking the average of them. And the exact same relationship is going to happen right over here for this angle that we've got labeled as y. Y relates more directly to this B arc over here, and of course remember this is y as well because of vertical angles, and D. So in the same reasoning that we just did with x here a moment ago, y is going to be the sum of B and D divided by 2 as well. So the measure of angle y is the sum of those two arcs, B and D, and then we're going to divide that by 2 as well. So this is a little harder than central angles, where y would just equal b, and it's a little harder than inscribed angles, where y would just be half of b. Now y is going to be the average of b and d, and likewise x is going to be the average of a and c. All right, so let's see that in action here. In this diagram, we have ourselves an angle whose vertex is not at the center of the circle, nor is it on the circle itself. So this is what happens when we have two secants intersecting inside of a circle. So the theorem we just wrote down said that the measure of the angle formed, which in this case is going to be a 5x plus 2, is equal to the sum of the two arcs that it intercepts. So that's going to be the 8x plus 3 above it and the 4x minus 11 below it. And then all that gets divided by 2. So we are going to take an 8x plus 3 and add to that a 4x minus 11 and then divide all of that by 2. And that is the setup here. Now our strategy for how to solve this might depend on how this right side numerator works out. So let's see. We're going to combine some like terms here on the top. The 8x and the 4x are going to make a 12x. We've got a plus 3 and a minus 11, which will combine to make a minus 8, and we're dividing all that by 2. And we got lucky here. Since both the x term right here, the 12x, and the constant are both even numbers, dividing them by 2 isn't going to be that bad, which is good because I'm almost running out of space and I'm not sure how to extend a page on this thing. I'm using a Smart Notebook app on my iPad here, so we'll see how this goes. The 12x divided by 2 then is going to get us a 6x. And the minus 8 divided by 2 is going to be a minus 4. And now everybody from here, I'm thinking we know what's going on. We're going to bring the 5x over here to the right. So 6x minus this 5x is going to give us just a 1x. We're going to take the negative 4 and add it to the other side, and we're going to get x equals 6. That should be our solution here, everybody. But let's double check that. And if we were going to do that, we'll go green here and see what we can measure. If x is 6, let's do a few things. This angle right here in the middle, 5 times 6 is 30, plus 2, that makes that a 32-degree angle there. And as far as the arcs are concerned, 4 times 6 is 24. 24 minus 11 is going to give us just a 13-degree arc right here. But up on the very top, 6 times 8 is 48, and 48 plus 3 is going to be 51. It's there somewhere. 51 degrees, everybody. I'll write that here. Now, I don't know if that makes a whole lot of sense, but if we add the 51 and the 31, that's going to get us a sum of 64 degrees. And if we divide that by 2, that gets us the 32-degree angle that we thought we had right there in the middle. So I feel pretty good about that answer. Okay, moving on to the second theorem now. This one deals with, and here's your important word now, what happens if you have two lines intersecting outside of a circle. So in this theorem, we actually have three different cases of it, but lucky for us, they all use the exact same formula. So in case number 1 right here, this is what happens when you have two secant lines intersecting outside of the circle. Now that angle right there creates actually 4 arcs on the entire circle here. Here's 1, here's 2, here's 3, and here's 4. But the only two that we're interested in this formula right over here are the arcs that right here we have labeled as A and B. And those are what we call the included arcs, meaning that they're included inside of the angle formed by the two secants. And in this case, you'll notice that the formula here looks almost identical to the one we dealt with in Theorem 1213, except now we are subtracting those two arcs right there instead of adding them. So what we're going to do here is take the measure of arc A, which is always going to be the larger of the two included arcs, subtract the measure of arc B, the smaller one right there, so A minus B in the numerator, and then divide that by 2. In the second case, which is located right down here, this one is what happens when we have one secant line right here and one tangent line. But again, the important thing is that the intersection of those two lines right here is located outside of that circle yet again. Now in this case, that angle is going to create 3 arcs. A and B are once again your included arcs, and then you have this one out here which is excluded, and we don't use that one at all. And the formula right over here is identical to the last one. X, which is the measure of our angle formed, is equal to A minus B, the difference of the two included arcs, and divided by 2. And I thought there was a way to scroll this thing, and that's not working. Wait a second. There we go. Okay, and everybody, here we go back to our third case right over here. This is what happens when you have a tangent line and another tangent line, and again they intersect outside of the circle. So this is similar to the ice cream cone theorem we talked about last week, back when we were actually in school, except that one dealt with the lengths of segments, and this one deals with angle and arc measures. Now, two tangents are only going to create 2 arcs. This larger major arc here, which is labeled A, and this smaller minor arc, which is labeled B. All of the arcs of the circle are inside or included within this angle. And lucky for us, third time's a charm here, the same formula applies here as well. X is equal to the difference of A minus B, all divided by 2. A couple of important things to note right here, because all of the arcs here are included within A and B, those 2 arcs right there are going to have to add up to a total of 360 degrees. So let's remember that. And again, A always is going to be the larger of the 2 arcs because it's located farther away from the angle itself, located right over here. So it's important that we do A minus B rather than B minus A. If we goof that up ever, our measurements are all going to come out negative, which certainly can happen. So that's really just one theorem, but with 3 different cases. Okay, and let's see that in action here in this case. All right, so the important thing to note here is that the intersection point of our 2 lines is again outside of the circle. So which of the 3 cases from over here that it was isn't really relevant, although it looks like this is the second case where we have one secant line right here and one tangent line. Now there are 2 arcs that are included inside of the angle. We have this larger arc right here, which is 150 degrees, And then we have this arc right here that I've highlighted in green. And of course, the hard part here is that we don't know the measure of that angle. So, in order to figure that out, let's be aware that there are 1, 2, 3 arcs total on the circle here. And the 150 plus the 140 is going to make a sum of 290 degrees. So, knowing that the whole circle is 360, we'll subtract the 290 that we have, and we'll get 70 degrees then left over for the measure of this green arc, which is the other internal one that we needed. So that is the information we had to figure out before we got started on this problem, and now we'll just work on translating the theorem from the last slide. The measure of your angle formed, which is x, is equal to the difference of your two included arcs, and it's always going to be the one that's farther away first, 150, minus the one that's closer second. So 150 minus 70, and that's all going to get divided by 2. And of course, you could put this in your calculator all in one step, but this one's not too bad. The 150 minus 70 gets us a difference of 80. Divide that 80 by 2, and x is going to end up having a value of 40. Let's look at a second example. This one deals with two secant lines now that are both cutting through the circle, intersecting it twice, but again, the important thing is that their point of intersection is outside of the circle. And in this case, we know the value of the angle formed right there is 46 degrees. And we've been given the measures, albeit in terms of x, of the two arcs that are included. So this one hopefully isn't going to be too tough to set up here. Let's see what we can do. Translating the theorem again, we always start with the measure of the angle formed, which in this case is known to be 46 degrees. And that equals, and here we go, this is going to be a big fraction now. We do the difference of the larger arc minus the smaller arc. So we're going to start with a 7x plus 11 minus, and this is really important now, anytime we're subtracting a binomial, we need to put parentheses right there at 4x plus 9, but as a quantity. And now what we're going to have to remember to do, everybody, is apply the distributive property on this minus right here. So the important thing there is that that 9, which appears to be positive, is actually going to be negative. Okay, so back to where we were here solving this. We're going to get a 46 is equal to, and we got a 7x minus a 4x, which is going to give us a 3x there. And this is a positive 11, but we're actually subtracting 9 from that because of the negative here. So the 11 minus 9 is going to get us a plus 2, and we're going to divide all of that by 2. Okay, for how to proceed from there, the problem we have right here, and it's not the end of the world, but it's not our favorite. We've got an odd term right here, 3x, and if we try to divide that by 2, we're going to end up with a decimal right here. So if we were interested in avoiding that, what we would do here, rather than dividing everything by 2, is rather to multiply both sides of the equation by a 2. I didn't leave myself much room there. And what that's going to do is that this 2 and this 2 are just going to wipe each other out. So, what does that do for us? The 46 times 2 on the left is going to give us a 92, and that's going to equal a 3x plus 2. We're then going to subtract that 2 from both sides here, and get 90 is equal to a 3x. And lastly then, we'll divide by 3, and we'll get x is equal to 30. So there's our solution. Let's check that and see if it works out well for us. Ooh, let's pick a... Ooh, I like that gray. All right, we'll go with that. So if x is 30, let's see what we have here. 4 times 30 is going to be 120, plus 9, that's going to be a 129 degree arc right there. 7 times 30 is going to be 210, and 210 plus 11 is going to be 221 degrees. If we think about the difference between those two arcs, 221 minus 129 right underneath that, that's going to be a 2 and a 9, so that is a 92 degree difference, and this angle right here is supposed to be half of that difference. And sure enough, half of 92 is 46, so that answer checks out as well. Okay, last example we have for today here. All right, this is really the third case here where we are dealing with not just one tangent, but two tangent lines here. But, like before, the important thing is where their point of intersection is located, which is right here outside of the circle. Now, what a lot of people don't like about this problem is the fact that there are three quantities that have to go into our equation. And we know that the measure of our angle formed is 35. We know the measure of the smaller interior arc is x. We were not given the measure of this larger arc here. So, the key to a problem like this is to realize that unlike the last two, all of the arcs that make up the entire circle are relevant to this equation. We know that this arc right here in yellow and that this arc right over here in green make up the entire circle and have to add up to a total of 360 degrees. And so, if we know that one of the arcs that we were given is x, the other one simply has to be 360 degrees minus whatever we were given here for the first arc. Now, if you think about that in terms of constants, if this arc right here was 100 degrees, then 360 minus 100 would get you 260. It works, and it works just as well when we've been given an x. So, with that in mind, let's go ahead and try to set this up. The measure of the angle formed, which is 35, is equal to half of the difference of the included arcs. We start with the larger arc that's farther away, which is 360 minus x. And it's not necessary, but I'm going to put a set of parentheses around that, minus the measure of the closer, smaller included angle, which is just plain x. And since that x is a monomial, we don't need to put parentheses around that, and it all gets divided by 2. Okay, so 35 is going to equal, and here we go, we've got a 360. Now, right here, everybody, we had a minus x and another minus x right here, which are going to combine to make a minus 2x, all divided by 2. And once again, we've gotten lucky. We've got an even term here and an even term here, so I don't have a problem simply dividing that by 2. 35 then is going to equal 360 divided by 2 is a 180, minus a 2x divided by 2 is just an x. We're going to bring that x from the right over to the left. We're going to subtract the 35 over here, and we're going to get x is equal to, should be 145 for the measure of that arc right there. Okay, so let's see if that works out. This arc is 145 degrees. 360 minus that 145 is going to give us 215 degrees. If we took the 215 minus the 145, the larger arc minus the smaller one, we're going to end up with 70 for the difference between these two arcs right here. And then 35, sure enough, is half of that difference that we just came up with. So again, the 145 checks out as well. I don't know what that does. Okay, it does that. All right, everybody, so that's a wrap for 12.4, Part 1.